So we continue hit Markov model. I'll touch a little bit on the training part again, do a bit recap, and then we'll move into the actual recognition process. We'll few lectures talk, later on, language model, those type of methodology later on. So again, learning hidden Markov model, the parameters, again, we have to use practically this Bayesian estimation or maximum likelihood estimation. But the problem is that data likelihood function is incomplete. We don't get a global solution, so we have to do some iterative processing. So that iterative process we call expectation maximization. So the HMM needs to be learned in the EM fashion. So again, repeat, we'll do a review. So you have observational sequence. These are essentially the sets of data you collect, and you extract the features out of this data. So those are sequence of observation. Q are state sequence that are open hidden to you. You really want to find the parameters of the data that maximize P of O given lambda. Okay, so but we don't really know what the Q is, so there's no way that we can optimize this function directly. So what we do is say, okay, assuming we do know what Q is, imagine Q is a random variable, right? So knowing the relationship between O and Q under this particular lambda, and then we define a Q function on this particular data likelihood function. The Q function is this thing, sum over all possible state sequence, right? Imagine Q is a set of random variables. Okay, imagine sum over all those possibilities of your state sequences, the log of P O Q given lambda multiplied by the probability of O Q given lambda prime. Okay, so again, look at this. This is a function. Okay, log of a random variable. Okay, multiplied by the probability of that particular random variable. Okay, sum over all possible cases this Q could take. Okay, this is like an expectation operation. So P, imagine this is a function on a random variable is a random variable. A random variable is a function. So a function on a random variable is also a random variable. So this is like expectation. Sum over all possible cases this particular Q can take. So you're taking out the randomness in this Q by taking the expected value. Okay. But we don't know this P probability, so here we have a guess model. Okay, so essentially we're trying to find this Q function of the actual true parameter and the guessed parameter. Okay, so we want to make sure every time we get a new guess parameter, this particular Q function can be optimized. Okay, can be maximized. Okay, so that's the expectation maximization procedures. So we can, operationally do this thing, right? Given a particular state sequence P of O Q given lambda, you can write it as, initial state probability at time 0, your Q, whatever that state is in, multiplied by T from 1 to T, right? The entire sequence of that particular sample of the speech. A QT minus 1 times QT, right? It's our basically transition probability between the state at time T minus 1 to the state at time T. And also when you're in T, right, what's the probability that you see the observation of all of T, right, and multiply them, okay, because it's a joint distribution factors into product, because once you know this transition, okay, this is first order Markov, everything else is independent from that. So this Q function can then be written as this form, right? Remember, the Q function is a log on this complete data likelihood function multiplied by the probability under lambda for a particular guess model, okay, and sum over all possible Q sequences. Okay, so when we write this Q of lambda and lambda prime, right, sum over all possible Q, right, and then we plug this back in here. These are the true parameters, right? So and then because the log this term, and this term, right? This three product term now becomes a summation. Okay, so you have sum over all Q log of this pi Q0 multiplied by a number. Right? This is actual probability value you can get because you have initialized the parameter using segmental k-means. Okay, so you actually compute this number. This is constant. This is the function sum over all Q. Sum over all Q, sum over all time. Okay, the log of the transition probability of time of the transition between Qt minus 1 to Qt multiplied by a constant. This is a probability, right? P of O, or not constant, a scalar, right? A number, just a number. P of O Q given the current guess model. Again, also sum over all Q, right? All possible cases through the sequences the log of the output probability at particular time you're seeing on the observation and multiply by a scalar, okay, the probability under the current model. So you have this Q function now being factored into three different summations. Okay, so I want to find the set of lambda, right? Set of lambda, right? These are the true values that maximize, okay, this particular function. Now we can individually work on this thing, right? So we want to find what pi sub q naught, okay, well, should be so that this entire function will be largest. Okay? We want to find what that a qt minus 1 qt should be, okay, so that this entire three-dimensional function will be largest. Okay? We want to find a set of parameters with this output probability distribution be such that this entire Q function will be the largest, right? So you can solve them individually. Okay, so then you can optimize the parameter independently, right? The first term, right, sum over all possible Q, right? So what's all possible Q, right? If you define your Hidden-Markov model with state, n different state, 3 state, 5 states, so basically sum over all possible things is just I from 1 to n, right? Log of pi I, right? Probability of all Q not equal to I, right? Under the current guessed parameters, right? This is the Q scaling. So now try to find a parameter that maximize this particular term, okay? D pi I, okay, because the rest of two terms will go to 0 because they don't depend on pi I. D pi I of this thing to add a Lagrange multiplier to make sure summation of all possible cases, this random variable, right? This parameter can take will always sums up to 1. Okay, so this Lagrange multiplier helps you to do that. And set this equal to 0 and try to solve what pi I should be, right? Pi I is the parameter you want to estimate. So the pi I now with a few algebra, you can show that the pi I essentially equals to probability of the observation. And the first initial state is in the I state, right? Pi I, the initial state is the I state under the current guess model. Okay, the model you already have some initialized parameter values divided by the total probability of the observation given lambda. Okay, right? So we get to compute this. We already know, okay, this can be computed by a combinations of forward and backward variables. Okay, so then you can get this pi I. Now, also with the second term transition property, right? Sum over all possible transitions could take, right, all the possible way Q can be, right? And then multiply by summation from t from 1 to t, okay, log of these variables and the probability scalar, okay. Okay, so all possible things Q can do these transitions, right? Q each one of the time it has n state that you can go to. So all 2 times you can have I from 1 to n, j from 1 to n, right? I 1 can go to 1 can go to 2, 1 can go to 3, right? 2 can go to 1, 2 can go to 2. So all these possibilities are going to be summed up here, okay? And also sum up the probability and sum up the entire sequence t from 1 to t. Okay? Log of aij, okay, probability of all qt minus 1 equals I, qt equals j under the current guess model. Again, similarly, you want to do a constraint, okay? Summation of this aij has to be equal to 1 because that's a random variable. Some all possible case that it could go, it needs to complete the entire sample space, right? So it needs to have a probability mass of 1. Again, the rest of them is simple. D, aij, D, this entire function set to 0 with the Lagrange multiplier, making sure that summation has to be equal to 1. Then you get this aij update rule. Okay, this is the parameter you want to update. Update with what? You update with this number. Okay, how do you get this number? Because you have the initial model. Okay, then you can compute t from 1 to t, the probability of the observations, and look at at the particular time, right? T minus 1 when it's in I, and t is in j. Okay, divided by t from 1 to t, probability of O q t equals to I. So basically, this is a ratio between you're going out from I and landing in J, right? So that's become my aij. And this probability we can compute using, again, some massage versions of alpha forward and backward variables. You can define these eta functions, and you can actually compute these numbers. Okay, these are actual numbers you can compute that base off the alpha and beta variables that you we learned in the forward and backward algorithm. Okay, so again, the process become very straightforward, right? The HMN, you need to have a model to start. Okay, how do you start to segment k-means? Okay, assuming a Hidden-Markov model left to right. So you segment your utterances into equal size chunk. then you assume the state is 1, 1, 2, 2, 3, 3. Okay, then collect for each of the class the same state. Look at those features through a k-mean clustering, then you have a initial parameters for your all these things for b of bj of ot. Okay, once you have that, then you have the initial parameter set here. Okay, then what you do is start computing, right? You just need to compute those alpha and beta variables and actually get this number. This new number become the best guess number for aij, because by plugging this number become the aij, you optimize the Q function. Okay. Now the next time around, you have a new guess model, recompute this, update this aij. Okay. Then you have a new aij. Now you have a new guess model, recompute this, and you update this aij. Okay. Every time you do this, you iteratively optimize this Q function. And the Q function we call expectation maximization. You're doing a complete likelihood. The complete likelihood essentially is the expected value over how these particular parameters can take on average. Okay? And you want to maximize the probability that these parameters taking on average of these values will be maximized. So in that particular process to find the parameter. Okay, the Gaussian mixture model, how it fits into the space. Okay, again, can imagine that the output probability is the Gaussian mixture model. And what is a Gaussian mixture model? It is a mix of Gaussian. So it's a summation of Gaussian. Okay, so it basically, but you don't know which Gaussian that it is, right? So the mixture weight is unknown. Okay, so you have n mixture that compose of that Gaussian mixture model. So your this Q function, right? Assuming you know which Gaussian that it comes from, right? So again, you take the expected value, right? Some overall cases that this mixture can have, right? You have 32 mixtures or 16 mixtures. You don't know which data comes from which mixture. Is the same thing as you don't know whether the data comes from which state. You don't know, okay? But what you can do is say, if I assume I know, and I actually can compute the probability under the current model, what that is, okay, that is the probability. Then we take the average of that, take the expected value of that, and try to solve what the parameter value should be, so that I can maximize this Q function. It's the same process. Okay, so not knowing state, you assume you know. Not knowing which Gaussian, you assume you know. Okay, once assume you know, but you don't know what to maximize, you maximize under the current parameter values, taking some overall possible values those things can take. This is an expected value maximizing the Q function. Okay, so that's what's EML. Repeat. So we have, again, some overall possible Q, and you don't know some overall possible N, which make sure that it actually comes from, right? So your this kind of the Q function, the complete analytic function now has O, Q, and N, right? The hidden state, okay, which make sure it comes from under the model, okay, multiply under the guess model your O, Q, and N. Okay. So M is just a vector that indicates the mixture component for each state at each time. Okay. Now we can explain the equation just like before. Okay, again, sum over Q, sum over N, sum over T. Okay, log of B, Q, T, O, T, F, Q, Q. Okay, multiplied by some scalar. Okay, this is a number that you actually know. Okay, so again, how we explain that? Again, sum over all possible Q's, right? Basically, sum over all I's, sum over all M's, sum over all T, right? This indicates the total possibilities of mixtures, total possibility of the state sequence for one utterance entire sequence, okay, the NT sequences, right? So this tells you time, this tells you mixture, your Gaussian mixture model, this tells you the state number, with sum over all possible cases. Log of the weight, right, under the state for which mixture, okay, this is a number, okay, so this number, if you add up all the mixture, it should sum up to 1, okay, right? So CIL, BILOT, okay, probability of O, QT equals 1, and QQ equals L given lambda. And we know this BILOT, right? This is a weight, okay, of each mixture, of each state of that mixture, okay. Then this B is just a Gaussian distribution, right? Under that state for that particular mixture, it is a Gaussian distribution. It only depends on mean and variances here. So a Gaussian mixture model is no more than a weighted Gaussian add up. So this you can rewrite this BQT OMQQ is a Gaussian mixture form as this particular version. Okay. Now again, the rest of it is simple, right? So you just basically do DCIL, that and cyclosterol and so, okay, or DML and cyclosterol, D sigma IL. And these are the three parameters we want to do, right? For each of the state for that mixture, okay, what's the weight? For each of the state for that mixture, what's the mean vector? For each of the state for that mixture, okay, what's the covariance matrix? Okay, right. So for each of the state for that mixture, what's the weight? Okay, again, you just sum over the probability. Now you're in that state. Okay, the mixture is a particular L mixture. Okay, under the current guess model, the sum of t from 1 to t is L from 1 to L. Basically, you sum over all mixtures, right? These two terms are the same. Here you just sum over all mixtures. The P of in the I state, okay. The mixture again is L, but you sum over all of them. So it becomes a ratio of the probability that you are in that state and you're in that mixture divided by you're in that state and you're totally in the entire mixture. So this gives you a weight of that mixture weight within that state. Again, this can be computed using, once you derive those four backward variables and the gamma variables that you have. The Gaussian mixture mean updates, okay, it's very similar. Reflected this is set multiplied by an observational sequence. So again, the observation, okay, under this state of this mixture, right, multiplied by the weight and divided by the total thing, okay, it gives you again eventually what the mean of the state and within that mixture, okay. And similarly here, right, this is just a regular covariance matrix operation, right? So observation minus the mean, observation minus the mean, take the transpose, right? This is just covariance definition. Okay? This multiplied by the weight of this thing within the I state in the L mixture, okay? Divided by, the total I state in all the mixtures. Then this particular weighted ratio multiplied by the covariance matrix become the estimate for the true covariance matrix under that state for that mixture. Okay, so the idea is very simple. It's all about weighting, counting, okay, and then see, okay, how much this mixture account for everything, how much this state account for everything. Okay, if it does, then you just multiply to either the feature value, and that sums up to average, or you multiply by the actual covariance matrix. It becomes the covariance matrix used for this mixture and for this state. Again, this thing repeats, right? So again, once you do one update, right, you have for each of the state, which make sure you have a new weight. Each of the state have for each of the state, each of the mixture have a new mean. Each of the state, each of the mixture have a new covariance matrix, and all these three things involves in computing this. Okay, then you repeat this process. Okay, so every time you do this thing, you're gonna automatically update all these things. So you put it all together, right? You have this thing you want to update. Okay. You have this thing you also want to update. So there are two of these equations, and you have three sets of these equations. Okay, basically these are the 5 equations. You do it iteratively, updating your HFN GMM model. Okay, and you do it when you see one example. This is the thing you compute. Okay, to get the new next one. And then if you do next iteration, you recompute this. Okay, that was for one example, right? You have one training instance. That's what you compute. Now, if you have multiple training instances, say go out collect for each of the class, 10,000 hours or 10,000 samples. What you do is basically just expand it to additional summations, because we always make a very strong assumptions that every training sample you get, they are identically evenly distributed. So when you have jointly looking at the entire data set, it's a joint distribution of all the data you have. But because you assume their IID, so basically the joint distribution becomes a product of every sample's distribution. Okay, so originally you have this thing, right? Now what you have is n samples of the observational sequence. What you have is just multiplying this log of all k q lambda multiplying k n years. Okay, so it's a very simple concept of joint distribution of all the samples you collect. Each of the sample has a complete data likelihood function. Okay, and because every sample we treat them as independent, so all this joint distribution now factor into product. Now you can again redefine your Q function. It's still the same thing. So you just have a summations of all of this thing that then multiply each other. Okay, so again, we are still in the space of finding the expected number of times, time state I time t minus one aij expander of number transition from state I to j divided by expected numbers of transition out of state j, the state I, sorry, the bj of is just a Gaussian mixture model sum from k from 1 to m ijk and normal distribution observation on the left state that mixture, Covariance matrix on the left state that mixture. Okay, so again, the formula doesn't change except that you have additional summation here. Okay, summation over k utterances, right? To update expected number of times in state I at time t equal to 1. Originally it's just this. Now you have k utterances, just add k utterance, sum of k utterances. Okay. Now the gamma is just this p of qt equals I equal O lambda. O and lambda is just alpha, the four variables of the k utterances at time t of the state I, right, multiplied by the backward variable of the k utterances time t, okay, of I, and divided by total probability of that k utterances. Okay, and all these things, we just sum up k times. Okay, so for each utterances, you have a alpha variable and beta variable for the utterances. And once you have those things, then you can compute this gamma, okay, and also this eta that tells you between I to j, right? So four variable backward variables, it goes from I to j, right, multiplied by bj at this time, and then your j, and then total probability of the observation for that particular training instance. Okay, so and then these are all things you can compute. You just need to compute for every utterances. Okay, every utterance has a forward variable, backward variable. All these things can derive this gamma and also this eta. This thing will plug it back in here so that you can actually compute this thing. This becomes a new update to move on to the next iteration. Okay, so when you have n utterances, it's just basically a summation over more stuff. Okay. For Gaussian mixture model updates, when you have multiple utterances, still the same, right? So for when you do this, you have this gamma t j k. This term is the same term as we had before, right? In the previous one, right? Just tells you what's the probability that you're in state j at time t for what utterances. Okay, divided by total, right? So this p of O given lambda. This tells you what's the probability that t equal qt equal to j, and then the entire observation is O. Okay, then you also additionally multiply this thing. Okay, tells you which k that Gaussian mixture model is accounting for the entire Gaussian mixture model. Cjk normal distribution, sum from 1 to m cjm, and the normal distribution. Basically, the entire mixtures and the one of the mixture. So these variables are going to be used in terms of these updates. And we have multiple utterances. What you need to do is just sum over all those utterances. All right. So again, hopefully this is a lot of mathematical symbols, but if you think about the concept, it is somewhat straightforward. Okay, it's just that I don't know what Q is. Okay, I also don't know what Gaussian mixture model, which mixture is generating my utterances. So what I cannot actually compute the complete likelihood because I have something I don't know, because those are random. Okay, I don't know which state I'm in. I know a probability distribution of my state. Okay, I know a probability distribution of my observation. So there's nothing indefinite I know. So there's no way I can directly optimize this. So what I can do is say, okay, if I do know one thing, okay, then I can compute the actual, right? If I know it's coming from state 1, I know it's given by mixture 1, okay, then I can compute the actual probability, basically collective of that feature. But since I don't know, so what I would do is I will sum over all those possible Qs. I will sum over all those possible M's, okay, the mixtures, and then see under those cases, what's the probability of me seeing this observation. I want to find the parameters such that this expected value will be the largest. That's why it's called EML, again repeat. Usually we just say maximum data likelihood, right? So it's MLE is basically saying if I can find a set of parameters, it'll generate a feature that I have. Okay, I find the parameter equals something so that the feature value is most likely to occur from this model. Because I don't know Q, I don't know which mixture, so I have no idea to compute actual data likelihood of this feature because all of them could possibly generate my O. So what I can do is assume I do know, assume I know it's from state one, I assume it's from Gaussian mixture model, the first Gaussian. I see these MFCC features. Okay, if I know these answers, then I can compute a number, right? That's a data likelihood. So I can pick which Q and which M of those parameters, the parameters of those Qs and M's such that I will maximize this feature, maximize the probability I see this feature. I don't know Q, I don't know M, so what I can do is say, okay, they're all probabilistic generated, so I will look at all possible ways, okay, my HMM would generate my features, okay, so I will sum over all possible states. I will sum over all possible mixtures, okay, and then I weight it by the possibility of them occurring, okay. How do I weight that possibility is the current guess model. So now it's a weighted, right? It's a weighted sort of expectation to tell me, okay, on average, if I am right about my current model, this is on average, okay, I will see this probability of me seeing this observation. Okay. Now my goal is to find a set of parameters, okay, such that this kind of on average probability will be largest. Okay, so you find a new set of parameters so that, okay, on average, if I see this observation is even more likely, can I move my parameter space in a way that I always find a new set of parameters such that on average, under the current guess model, I'll most likely see the observation as. Okay, so that's the intuition behind this, and then it eventually boils down to basically 4 or 5 formula lines. Okay, and within this, it really only depends on this alpha and beta variable. So it really boils down to what we call the computing forward and backward variables. So we call forward and backward algorithms. And this kind of particular algorithm, then we call them Baum-Welch re-estimation. Okay, so this Baum-Welch re-estimation by coming from the finding the alpha and beta, this forward backward algorithm, and using forward and backward algorithm to do this update. People do find that it's basically a specialized version. Okay, it's a special case of expectation expectation. You get the same answer by treating this as an EM algorithm. Okay, or you directly say, okay, use this alpha beta variable as a way to re-estimate the parameters I want to get. So yeah, HMM learning. Okay, that probably concludes it. Okay, so we talk about HMM, the basic 3 questions, right? You can now should be able to answer right the probability of observation, okay, under the current model for an HMM. So what you need to do is basically somewhat compute forward backward algorithm, the variables and sum over any time instance they're all possible states, all possible state counts, and sum it up, then you get the total probability. You also have a process of finding the best state sequences we call viterbi decoding, right? So as you move down the chain, okay, as you move down this kind of one step by one step, every state, every time, you look at, okay, you store the maximum probability I reach here, and also store if I were to reach from one of the 3 previous state to this particular time, this state, which one I have come from. Okay, so every time you store a variable that gives you the maximum probability of landing in that state, and also tells you where I have come from. So if you do that iteratively till the end, okay, of course you can backtrack. Okay, you can say, okay, at the end I see which state is the largest value. Okay, that's the largest one. I look into it and say, okay, if I am the largest probability, would have given me that largest probability. I can go back and retrace it back. Then you have a trace of most likely state sequences. Okay, so that's viterbi decoding. Okay, trying to find the maximization, right? Maximum over all possible state sequences that give me the observation. Viterbi decoding tells you that, right? Give me a state sequence, a line of sequences of Q that would give me the maximum probability of my observation. So then, in the third question is the learning of this parameter. Okay, so these are again over all these times we're basically telling you, okay, do EM algorithm try to re-estimate this Okay. Now we can move into the actual recognition part. Okay, let's start simple. The isolated word recognition or isolated entity like one, then you stop, two, then you stop. Uh, so you assume V is a vocabulary of words, okay, a set of all possible words to recognize. Say, for example, you're designing a digit recognition. The total possible single digit you can have is 0 to 10. Right? So you have a finite set of words that you can recognize. And for each word, you can train a unique DHMM model. Then you say, okay, to train each model, you can use multiple say K training utterances. For digit recognition, maybe you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, okay, or 10, right? So in this case, you have 11 models. So you have 11 models. These are single digit or single, we call it isolated word recognition, okay? Given a particular speech file of unknown utterances, okay, you just compute the P of all given lambda, and then there's a lambda here, there's a lambda here, there's a lambda here, there's a lambda here, compute reflecting each one of the lambda, okay? And then what you do is pick the one that gives you the largest P of all, okay? That's a very simple, we call it classification problem. So at recognition, very simple, you just say probability of all given lambda V, okay, for each V. And we know how to compute this, right? You just need to compute forward and backward variables and sum it up. You get the answer for each of the model parameters. Okay? Then we see, okay, under this model, okay, you may have a largest probability. You pick the model, you pick the vocabulary, pick the word that gives the largest probability, and done. Okay, that's the simplest classification task you can think about, right? Single digit isolated word, nothing is connected. Okay, and then you practically can just train HMM for each class. Okay, we'll look at a more complicated case called connected word recognition. Okay, this is where the actual speech recognition usually form, right? Because the way I'm speaking is a connection of words. I don't just speak a single word. Okay, I speak a connected word. Okay, then how do we do that? Okay, so we can formulate a problem like this. So if you have WI, either V, you word strong for vocabulary V of size NV. Okay, so you have NV set of words. Okay, each of WI indicate okay which word that it comes from. Okay, and utterances essentially is a sequence of words, a connected word. So if you have a sentence, is basically a sequence of words. Now, given an utterances of T frames, okay, the frames correspond to your MFCC computation. Okay, you decide your window, your overlap. Okay, and then it tells you how many feature sequence you actually get from your input speech signal into MFCCs. Okay, so what we need to do is we should find the word sequence that maximize the probability of the observational sequence. Okay. So WT is the W1, W2 to WQ. Okay, be a set of candidate word sequence. Okay, Q is the number of words in time T. So we basically need to find the most likely word sequence, P of OT given the word sequence. So let's by trying to compute this probability. Probability of A is a maximum over OQ, right? The principal word sequence. Okay. Out of the words, okay, which of those things give me the largest probability? Okay, so again, you have these connected words. Okay, so every connected words, okay, we need to find the set of connected words, okay, such that it gives me some largest probability. Okay, so I will decode that as my entire sequence. So we can kind of see things like this, right? Time over time, right? 1 to T, these are your MFCCs, right? So Q indicates the which word that come from. Okay, which word I come from. So we need to know every time at every time frame. Okay, the Q is the index of which word is most likely to come from. Okay, so we need to find this 1 or 2 or 3. Okay, all this may be 1, 1, 1, 2, 2, 2, 3, 3. So then, if we do know this is the largest, basically then we can say, oh, this is W1, okay, this is W2, this is W3, this is WQ, and these are the Q words. And you get a set of word sequence, okay, that maximize these observational sequences. Okay, so again, so you have time 1 to T observation from O1 to OT. Okay, at every frame, you have to decide which word that it has come from. Okay. But within every word, right, is a composition of phonemes. Okay. every phoneme is a composition of a three-state HMM. So what you're essentially doing, right, is those HMM state sequence decoding. Okay, finding the most probable state sequences. Okay, and understand which state it has come from, which phoneme is likely come from. Okay, which phoneme is likely come from, and those phonemes are going to be pulled together and know which word it has come from. So the dictionary will tell you these are a set of words. If you put these three phonemes together, this is the word. If you put these three phonemes together, this is that word. Okay, so every single point you have a state sequence decoding, but if this is a state one, most likely because it may have come from the state one of a phoneme two, right? Or a state two of a phoneme two. Okay, then that means these two frames all most likely come from the same phoneme. Then all those same phonemes, you put it together, it becomes the same word. So that means all those frames likely come from a set of words, the same word. Okay, then you basically try to decode all those things. So imagine this decoding become very big, okay? Because at every step of the time, you have to decode all of the HMM all together, right? Because think about originally in the Viterbi decoding, we only have one HMM. You're trying to decode. So what you do is say, okay, for every time, for every state, I'll compute the probability, and I also compute the maximum probability I reach here. Okay. Now, because all this entire sequence, okay, you have 40 something phonemes, for example, for a language, you have 40 phonemes. So at time one, okay, you have 40 phonemes, models, HMM simultaneous to start decode. Okay. At the next time, you'll see, okay, whether the phoneme one, okay, time two, whether that state sequence has changed or not, because phoneme one has three different states, right? So first phoneme you have three states at two times, right? The second phoneme also have another three states at every time. You want to see all this connection, right? At time one, okay, one phonemes and then only one, and then time two, the second phoneme, and then look at each of the state, what probability is the largest to have reached here. I also need to compute the probability that give me the largest one and where it had come from. Okay, through every state, every phoneme, every time. Okay, so all these things has to be simultaneously decoded until you reaches the end. Okay, then you know which one is the largest, you backtrack this state probability. Okay, once you backtrack this state probability and then you find a sequence of state, then you say, okay, I know these are the set of states that gives me the final largest probability, and these states correspond to that phoneme. Okay, those phonemes put together correspond to that word. Then you pull together those words, then becomes a connected word recognition. Okay, let's do that formally as mathematics. Okay. So again, the way to understand this is to understand Viterbi decoding. Essentially, we're doing Viterbi decoding, but we're doing cross all phoneme HMMs all together at the same time. Okay. So in practice, basically you kind of define intermediate probability. We call ATIV. Okay. So let's read off this thing. And that is the maximum probability of all passwords of seeing OP. And at this time T, the state is in I, given all password, and also the current word is B. Then you compute this for every state of a word at every time, and record a maximum probability value that the current time T out of all possible words, I T minus 1. That's basically what I'm saying, right? So you imagine this is basically an elaborate version of Viterbi decoding, and every time you need to know which state is likely, right? So every time you record that maximum, but you also know that particular phoneme or that particular word, okay, that state comes from a particular word or particular phoneme, okay, so you know at the same time that state is most likely, that also makes that word most likely, okay, and then you record that, okay, so and for every state probability you do it. So when you only backtrack until you hit the end of the sentences, okay, so for all that thing you have the entire very, we call it large lattices, okay. Across all models, all states, all time. You need to add every single time, every state for every model. You need to have a probability tells you that's the maximum probability I'm in here. Okay. I also record whether I come from which particular previous state, and also because I'm in that state, I also know, okay, because I'm in that state under this model, okay, I can know whether I come from that particular word or not. Okay, so again, so you have this index of the word index and also the Q index at the same time. And this is the maximum probability over all password of seeing things, right? So sum over I from 1 to NV alpha TIV, right? You sum up all the state, okay, of a particular word, but give me the maximum probability of that word, right? So because a word is being decomposed into different states, okay? This tells you every state under every word, okay, every time what's the maximum probability, okay, at that particular time. This then you sum over the states that compose of that word, right? That gives you again also the maximum probability of the probability that you are in that particular word, and then where you also have come from. Okay? So this is the maximum probability over all passwords in OT, and at this time T given a password, also the current word can be, and you try to find the most probable word at this moment given the possibility of the all password in one previous time. Okay, and then you kind of roll this thing out of B different words, optimal word sequence model until you reach the end, right? This is a capital T, right? Out of all the words, right? This is the vocabulary of V words. Out of the words, which V gives you the largest probability at the end, okay? And look at that. That's the one that gives you the maximum probability at of these four variables for all I, okay? Given a particular word, sum over within each word all the states, okay? See which one that is. So again, visualize V is the word, okay, with the model lambda V. NV is the number of states in each of the model. Pi IV is the initial state probability given word 1 equals to V, okay. BIV01 probability of observing the first sequence given that your state is in I and then your word is that particular word. Then you have this A1IV is just pi IV BIV01. P of A1 over V is just sum over I from 1 and V, this A1IV. Okay, so this is the P of A. Get this initialization. And the termination is again P of A is a maximum of over all possible words. Okay, PA, the final index T given V, and then again you find the word that actually gives you that maximum, and you backtrack the word sequence. I think you just the process is basically is a Viterbi decoding process, but now we're decoding through words. OK， 好，我用中文稍微讲，它会有点乱。它本质上就是 Viterbi decoding， 大家回头想 Viterbi decoding，Viterbi decoding 就是每个时间点 ，OK， 这个某一个 HTML model， 每一个时间点的每个 state 我要算它最大的几率，离它从哪边来。OK， 那我们一样 connected word 可以想象是有一堆 HTML，OK， 我同时现在做 Viterbi decoding，OK， 所以我在每一个时间点我看每一个 model， 每一个 state， 那个 state 它最大的几率是什么？它从来自哪边？那因为每一个 word 其实不同的 state 是组合 ，OK， 因为有一个 word 可以是有3个 state H 里面做，对，但我这个时间点第一个 state、第二个 state 跟第3个 state 都可能来自这个 word， 那我每一个时间点最可能的几率，然后我再把这一个时间点的，假如说我这个 model 有3个 state， 就把这3个 state 加在一起，就是我大写的 P， 所以你可以想象 word 其实还是在找 OK 每一个时间点最大几率的那个 word 是什么？那以及它前面可能会来自哪一个 word， 那就跟我在 state 里面也是一样，我在每个 state 我也是看着每个 state 我最大的几率是什么，我前面来自是什么 ，OK， 只是在这个 frame 的当下，因为这3个 state 都属于这个 word， 我就会把这3个 state 加在一起，变成属于这个 word， 那我一看这个 word 等于说，因为它都是最大的可能嘛，它没有别的更大可能，因为一路上来都是记录最大值，对，所以你一定是这个当下这个 word 最大值，也就是这个 state 所有可能的几率在这个最大值。所以这个 word 里面，你把这3个 state 加起来，也是这个 word 的这个时间点看最大的几率值。然后你也看 ，OK， 前面如果有个 word 要，我的 word OK， 因为它会来自，要么是前面的同一个 word， 或者前面的不同 word，OK， 那这边会有另外一个几率去记录我到底是来自前面的一个 word 还是不同的 word，OK， 那我就可以去说 ，OK， 当我到这个 word 的时候，我如果来自不同的 word， 是哪个 word 跳到我这边来？或者是我如果是比如在同一个 word， OK， 就比方说同一个 word 跑到我这边来的几率是最大的， 我就可以这样子慢慢的 backtrack。OK， 所以每一步你都往前 OK 再算，同时间我每一个时间点下每一个 HMM 的 state 的所有的几率是多少 ？OK， 拿这种百科比的方法去算 ，OK， 所以它就每一个时间点、每一个 HMM、每一个 state 它最大几率是什么？它来自哪里？然后因为每个时间点、每一个那几个 state 加在一起等同那个 word， 我可以记住那个最大几率是来自哪？是什么？以及来自哪里 ？OK， 然后这件事情 roll 到 t 等于大写的 t 的时候，我就可以去算 OK， 在某几个就看哪些风景或哪些 word model 加起来那些 state 加起来值最大，那就是最后一个值的最可能。然后在那个里面再去看我来自哪边，就可以 backtrack 出一条word state sequence。那个 best word state sequence， 因为你底层先做了这个 vector decoding 去找最可能的 state sequence。OK， 所以两个是叠加在一起的，大家想是叠加在一起的。OK， 但是我的基地其实就是在做 vector decoding 的。OK， 只是我同时在做n 个 word 的 vector decoding。OK， 那中间会有一点点小细节，所以我要怎么去看说我的 HMM， 因为我的 HMM 原本是一个自己 decode 自己一个就好，那我如果 n 个在同时 decode n 个的时候，我有可能会跳 HMM， 有的时候是这边会跳到这个 HMM， 跳到 HMM， 因为它表示不同的 state， OK， 细把连在一起。那这边我要怎么去？我们那边会引入另外一个机制分。Generally, just think about this is vector decoding. Okay, in your mind is always one HMM vector decoding is a time, right, and state. Okay, now you have connected word and you have time, state. Another model has time, state. Another model has time, state. Okay, then you have all those states. Okay, at the same time you do vector decoding across. Okay, so basically every frame, every time, because you're coming from the same model, you add up those probabilities. You have this large capital P, okay, because that's the largest one. Okay, under this particular word, okay, it cannot be any larger, so you can record whatever those states come from, which particular model. Okay, and you record that index as well, so you know at that particular time which that particular frame, okay, which word is most likely. So yeah, these are it's kind of a process. Keep that in mind. Okay. So you just bring the analogy of word is like a state and everything we talk about. Okay. The one thing we have to be aware. Okay. There are things that could happen, right? Two separate cases mentioned. Anytime t, right, as the frame goes, the model can remain in the same word, the same model, right? Or switch to a different word or a different model, right? So either at this time, okay, the largest probability that give me this probability where I have come from, it may have come from the same model, okay, the same model of the other state or same model of something else, basically the same word model, or I have come from other models and switched to my model, okay. So which one to choose? So this probability that every time we have to compare two things, okay, compare probability of PAT V at previous time is a same index, or the current time, okay, and the previous time, the word is not coming from the same. So we have to record which one is the largest every time to keep it, right? Okay, so in case one, right, so you stay in the same word, so basically it's simple, right, alpha t I v equals t minus 1. Same thing, okay, you just, you roll it, okay, you still sum over all the state, you have just switched from j to I, right, then you do this for all I, okay. In case 2, you're changing to a different word, so the model must have taken a change from the last state of a word to a first state of another word, okay, because our HMM is left-to-right topology, okay. So when you finish your HMM, you will jump, okay. So when you can only jump, when only you finish an HMM. Okay. When you start, you always start state 1. So the only possibility that the other word can jump to you is they finish it and jump to mine, right? So if the largest probability I will land in my first state come from the other model's last state, okay? If that probability is larger than the model I have remained in the same state of the same model, then I'll record that one instead of this one. Right? So that's when the transition can occur. So if your previous model at this particular time is not the same model as this time, then you have basically V1B. So again, you look at the maximum over all other models Okay, right? All the other models, that's not the same model. And they're in the last state, okay, of their model, okay, their four variables at those times multiplied by this probability P of V given WQ, okay, for I, and then if 0 and I not equal to 0, okay. We talk about this thing, okay, this is their last probability, at that time, okay, that other models of their last state. Now they have multiplied a probability and I find out which one is the max. I keep it, okay, multiply by now I'm in the state one of a new model because these are two different word models, okay. That transition, this thing, okay, we call it a language model, okay, because you have switched from a other words to this word, okay. If language doesn't matter, okay, all the words are equally likely to switch to other word. If this is uniform, you can drop it. It only depends on this thing. But if your language matters, okay, some word goes to some other word more likely to occur, then this is where you plug in the language model. Okay? So in a connected word recognition, okay, you're computing all these forward algorithms using vector decoding. But you want to tell at every time, I want to know whether if I'm in the first state, whether I'm coming from the last state of the other model, or I have remained in my same model of the same state of the first state. I can compute this, okay, that and this, which one I need to figure out which one is largest, okay. If this is largest, I'm in the same state, okay, same model, okay, same word. If this is largest, I'll record this because I have made a switch, okay. I make the switch, I know where I come from there, okay. And this particular probability will be weighted, we call this by language model, okay. And this P of V given past words, so we call P of WQ plus 1, and this is this word given all past words are W1 given WQ, right? Given all the past words of an artist is something, what's the probability of me seeing the current word at this time? Well, this is we call the language model. Okay, we'll talk in the next weeks, we'll talk about how do we actually estimate this. Once you estimate all those things, you plug this back in here, then you have a complete pictures of a connected word recognition. Okay. All right, so basically you put this thing all together, and we'll go through it because of time. I think we're up. So we'll cover this again. Again, if you look at this, these are probability. We're going to try to max. Okay, so every time you record where you have come from is the maximum. You backtrack and see the past words. 好，我们今天先我考了这类 OK， 我们今天教到这边呢，我下次会再回来稍微更正一下 OK。一样就 let us think， 其实全部东西其实你都学过，你要把它想成是扩张版，因为就是 the vector code 像不是做给 HTML 的 vector code， 你做 N 个 HTML 的 vector code， 那每个时间点，那我是那个 HTML 那个 state，OK， 那我都是取最大，所以我这个 word 最大几率就是这些 state 加起来的几率 ，OK， 所以我就可以用这样去找出最可能的 word sequence。但是有个没搞，因为我在这个时间点，如果是在第一个 state， 我有可能我前面的时候来自同一个 word 的同一个 state， 我才会跳到这个时间点，或者说我其实来自别人的最后的 state 跳到我这边来，那别人就是所有其他的 HTML，OK。那我走到说起来，就调这边来的几率，所以我就去看 ，OK。假如说我40个 HTML，OK， 我现在第一个，我在我第一个时间的第一个，我在 Q， 我在这个 HTML， 我现在是 state 是第一 initial 的 state， 我去看其他39个，它的最尾巴跳到我这边来，然后最尾巴跳到这边来，就是它已经有它的那个几率已经到它最后了嘛，所以它最后结束还有可能会跳过来，它没结束它不能跳过来，因为我们 HTML 有规定，它只能往前走。你一进来只能从一进来，尾巴只能从 N 出去 ，OK， 所以它必须到它 N， 它才能够跳到我的一。然后它跳到 N， 那我一中间过程又再乘上一个几率，那个几率就是 language model， 因为它要跟我来跟他说 ，OK， 你之前你在那个 state 最有可能，你在那个尾巴那个最有可能那个 word， 就跳到我这个 word 不是随时都可以跳，因为这个跳过来肯定有个 weighting 权重，你要比较有可能的 weighting 才有办法跳得过来，那个就是 language model。language model 整个 ASR decoding connected word recognition 是在那个 transition 里面，它会把它加进去 ，OK， 所以它会知道每一个在你的这个initial state 跟别人的最后 state 的 transition 过程中，这样的几率是多少？那它会去跟谁对比？跟我如果停留在同一个 word 里面，在同一个 state 里面去做对比，取最大值留下来。所以每一步骤你都在算每一个时间点、每个 state、每个 word 最大几率是多少，并存起来最可能来自哪边，一直到你 hit 到最尾巴。所以就有这个非常非常大的矩阵 ，OK。所以你看最尾巴哪个最大，你要来自哪个 word，OK。然后 word 从哪边来的，就这样子慢慢的像买这个笔一样，把它拉回去，那你可以找一个最佳的 word sequence。OK， 我今天先上到这里。